Just let me know if everyone can see this. It's good. Okay. So hello, everyone. Good morning. I'm very excited to be part of this webinar. I'll be talking today about the project that I've been working on for the last 2 years called Hydrolang, an open source web-based programming framework for hydrology and environmental sciences. My name is Carlos Erazo. I am from the University of Iowa's Hydroinformatics Lab. And I'm going to start right now by giving you some highlights on 4 specific topics, right? So the first one is the scope. In the previous decade, there's been many web applications for hydrological environmental sciences that are using native technologies. So by native technologies, I mean there has been improvements on the client-side hardware that enable faster computations using the resources available within. The second one is data. Well, where is the data that we're using coming from? Is it reliable? Which temporal spans are we constrained by? And more importantly, how can we access this data? This leads towards the literature. The review of the literature was based on the number of web-based applications and their native environment, in which programming language they're running. And afterwards, this arrived towards the objectives and implementation to develop a robust framework that can run on the client side for environmental problems. So this leads to the original research question, which was which open source web-based environmental hydrologic and hydraulic software libraries are in the literature and online. And this limited the research towards the similarity of the applications, which external libraries they're using and that are available for those applications. What are the architectural approaches for scalable design, and what kind of analysis are these applications running for? Thus, the main purpose for our project was to create a community-driven web-based research and educational framework that, first of all, uses state-of-the-art technologies. It's able to retrieve environmental data from open source APIs from around the globe, from around the world, is able to provide statistical analysis data, data cleaning, sorting, hydrological analysis, machine learning model creations, but it's not constrained by this. It's flexible enough to grow. It's able to deliver charts and tables directly from data visualization purposes, and renders different types of maps and layers. And this is Hydrolang. Hydrolang is a web-based programming framework written in JavaScript for environmental and hydrological data. It contains, as of now, 4 loosely coupled but highly extensible modules. It is available as a computational library, so that means that it has different functions, different modules and components. Each of them can be accessed through the core of the library. It is JavaScript based, so thus it requires to be served to a web browser. Importantly is that it's open source software under MIT license, and contributions are always welcome. The idea is that it's open source. Everyone can, if there is a specific functionality that is to be added into the main either of the modules or components, this can be done very easily by submitting a request or a pull request or a comment or any other type of reach out by to any of the developers. And this is you can see on screen the repository in GitHub where you can find the framework. So example of usage, specifically, as I said, it is served into a website, right? So this is mainly for applications that are running on the web browser. Thus, it is required as a module. Once it's unloaded, it is used as a variable. This variable contains all of the functionalities. So just to give you a highlight, it's running through this specific notation. So the class that is running this instance of the core module is can be accessed through the dot notation. So module, component, function, and afterwards the parameters that are running for that specific function. So in here I have 2 examples, one for data retrieval, and afterwards one for using that same data for the results to hydrological model for visualization purposes. On the right-hand side of the screen, I have the results of some data retrievals from different APIs. I think this one is from USCS, and the results from the visualizations afterwards running all of the analysis on the web. So we applied the software towards the CUAHSI Hydroinformatics Fellowship in 2021 and was awarded. And towards that extent, I want to highlight the work that has been done during the fellowship. So the objectives that the fellowship were entitled for were threefold. The first one was the integration of CUAHSI's APIs to HydroLang, as well as updates on documentations and software. First of all, HydroLang contains different data sources. So we have USGS, NOAA, FEMA, some Europeans, European, Australian data sources, Asian APIs as well. But we added from CUAHSI the Water One Flow, HIS Central, and HydroShare APIs for a fully comprehensive data structure that can be accessed through HydroLang's built-in functions for retrieval and storage. The endpoints on the screen are just some of the some examples of the ones implementing, allowing CUAHSI's data sources to be readily available through simple commands in HydroLang. The Water One Flow in particular allow us to access over 100 additional data sources of different variables within a spatio-temporal scale that gives us quick access to required information. Now, the second one was the implementation and usage of the basic model interface implemented by the community of surface dynamics on the JavaScript language to connect HydroLang with another coworker's web-based hill slope hydraulic model called HLM and deliver task on par efficient. So the work entailed integrating the interface in both projects to afterwards having HydroLang as a data source that connects and readily serves information from two national precipitation sources into the HLM and create floating hydrographs. So you can see on the right hand of the screen some of the example outputs from this project. Lastly, the project has been featured in the University of Iowa's hackathon, an event where students code different types of projects for 2 days straight. HydroLang was one of the main libraries for usage and expansion. The project will also be presented in AGU Fall 2022, as well as additional conferences with other projects featuring from the framework in the next years. So moving forward, I will mention briefly some of the expansion projects that are set in place to make the framework grow and become more appealing for web developers, researchers, and educators. We work on continuous updates for HydroLang, including new methods, functions, workflows, and modules to promote better collaboration for hydrologists and environmental professionals. HLML, which is the markup language interface for HydroLang, uses technology called web components to even further abstract the simplicity of using HydroLang through HTML tags. With the BMI specification, running well-defined sequential models becomes as straightforward as writing a configuration file and passing it to the framework that enables connection with other BMI compliant models and projects. Now, understanding the limitations of web environments, the HydroCompute library, which is a project that I'm working now, aims to use standards set in place for web browsers now for parallel computing and multi-threading to make then environmental analysis more appealing to be run on a web browser. Now, HydroLang Scratch represents a Scratch version of the framework where users can run simple interfaces by connecting boxes or another type of user availability through different functions. And lastly, we want to add NLP frameworks and natural language processing, so the users can run their commands directly through their voice. Main goals in future work, want to enable cross-platform open source environmental frameworks, position continuous presentations of the framework through new modules, and expansion in a community-driven growth approach. So with this, I leave the floor to the next presenter. If you want to reach me out, please reach out to my webpage. Thank you.
Thank you so much. Our next speaker is Shengyi Lin.
Oh, see my screen now? Okay. So hi everyone, my name is Zhongyi Lin, a PhD candidate at Lehigh University, and I just passed my defense last week. And it's very nice to have this opportunity to be here. Today I want to share a tool that I developed, a Python package of hydrological model for coupled nature human system, the HydroCNHS. As shown in this diagram, the HydroCNHS is an open source software to model complex adaptive water system. But what is the complex adaptive water system and why we need such a tool? And let me start our story. So in this anthropogenic era, most of the major basins involve some degree of human activities like the irrigation, reservoir operations, and urban drainage. And many studies have tried to investigate these so-called the coupled nature human system to better inform the management policy or simply advance the science. And here we further refer the coupled nature human system to the complex adaptive water system. In this area, one of the goals is to simulate the co-evolution between the hydrological environment and human system to capture the non-stationarity and the co-evolved dynamic in the real world. To that, the agent-based modeling, a bottom-up modeling approach, is a popular method to model the heterogeneous human actors' behavior, including the interaction with the changing environment, as well as other agents. For example, the agent here can be farmers that make the diversion decision according to the available water feedback from the hydrological environment, as well as other farmers' diversion opinions. So one way to model the complex adaptive water system is by coupling a hydrological model with a human model described by the ABN that we just introduced. And however, there's one largest limitations in the human model design and the coupling linkage that to build to integrate these two different systems. The design are often constrained by the structure of the hydrological model, and we want to overcome that. Therefore, we developed this package HydroCNHS, which have these four main features. First, we want the model to enable user to incorporate both exogenous and endogenous human components. Exogenous human components means that the user has the input time series data to represent human behavior in the simulation. And endogenous human components means that the user want to insert an equation or function into the model, and that the model dynamically simulates human behavior along the hydrological simulation. And second, we want the model to have a unified framework for calibration. As we have explained before, that this nature system and human system interact with each other tightly. So it is critical that we can calibrate this entire complex adaptive water system model altogether. And we want to ease the technical difficulty to integrate the user-defined human components into the hydrological model by providing this application programming interface API for automatic integration. And finally, we want the model to support the parallel computing for large-scale study. So essentially, this HydroCNHS is a semi-distributed hydrological model, which delineates a basin into a sub-basin, as I show on the map here. And in each sub-basin, we provide two different rainfall runoff options, the ABCD model and the general water loading function. And for the routing part, the routing describes the time delay for the water to transfer from the upstream to the downstream. And here we adopt the Lohmann routing model to simulate the within sub-basin routing and the inter-sub-basin routing, showing those yellow and the black dash arrows here. So to use the hydrosyn HS, user only need to provide 3 items, which show here. The climate data, including the temperature and precipitation. And the second thing is the model configuration files that contain both hydrological model setting as well as the user-defined human model setting. And lastly is the ABM module, which is the human model that programmed by users. So after we provide these 3 items, hydrosyn HS will go through the initialization and then coupling simulations, where the software will automatically incorporate the user-defined human component into the simulation according to the assigned API. To that, hydrosyn HS supports 4 types of API: the dam API, river diversion API, conveying API, and in situ API. They all have different coupling logic to incorporate different type of human component defined by users. To that, we use this example to explain how we can use this API to build up our system. Assuming that we have a water system look like this, and this N1 node is our outlet. We can use the dam API to incorporate the 2 reservoir into the system and use the river diversion API to integrate the irrigation district into the system, which this D1 can divert the water from this N3 node and have a return flow to this N1 node. And the conveying API can be used to describe the interbasin water transfer, as I show in this C1 agent. And it can also represent the pump facilities, as I show in this C2 agent, that will pump the water from the downstream N3 node to the upstream S2 node. And we also provide additional, there's another API I forgot to introduce. This in situ API can be used to describe the human component that can directly affect the runoff within the subbasin. And this can be the land use change or the drainage system. And we also provide 2 other additional features, which is the node group and institution for customizing this complexity water system. And for more detail, feel free to check out our online documentation. We provide a detailed documentation, including the basic hydrological simulation introduction and the step-by-step model building instruction, as I show on the slide here. So to give you a concrete idea of how we can actually use this package, here is the example. I used the Tualatin River Basin in the Northwest US as a demonstration. And in this basin, we have 1 reservoir, 1 pipeline for the interbasin water transfer, and 1 irrigation district. And they are described, their behavior are described exogenously and endogenously using different behavioral rules. And we can calibrate this entire complexity water system using the calibration module that provided by the hydrosyn HS, which is essentially a genetic algorithm. And after we calibrate model, here I show you the calibration result. And we can see that the model can capture the dynamic from both natural system and human system. The top 2 rows are the stream flow in different locations, and the bottom 2 rows are the reservoir releases and the irrigation diversion patterns. And hydrosyn HS is also a great tool for other advanced applications. For example, it can be used for exploring the coevolution between natural and human systems, as well as the uncertainty analysis. And feel free to check our publications to see more details. And as a summary, hydrosyn HS is an open source Python package with general public license that will guarantee you your freedom to share and change all versions of a program and to make sure it remains free software for all its users. And here I summarize some features that I mentioned earlier. that hydrogen that user freely incorporate exogenous or endogenous human components into the hydrological simulation. And we also support an integrated calibration module to calibrate the hydrological model as well as user-defined human model altogether. And we support the parallel computing for the large scale study. And this work has been published in the Journal of Water Resources Planning and Management, so feel free to check it out. And for the future, we will continue to evolve these hydro-CIHs. For example, we intend to add the sediment simulation module into this software, and we want to optimize the coupling simulation procedure to increase the computation node efficiency. And lastly, we want to provide some ASON for some predefined agent type. So we hope that by providing those options, we can better use this software to facilitate the education in the complex adaptive water system modeling. So feel free to check out our package on my GitHub. And if you have any question, feel free to send me an email. And I also list the reference, which including the publication for this software here. So this is the end of my presentation. Thank you for listening. And I will pass the mic to the next speaker.
Thank you so much. Okay, our next speakers are Jason Regina and Austin Rainey.
Hello. Got it pulled up, Jason? Cool. Can you hear me all right, Julia?
Yep.
Sorry, I forgot to click the right button. Let me try that again.
Wrong screen. Nice.
All right.
Hey, everyone. My name is Austin Rainey, and this is Jason Regina. We both work at the Office of Water Prediction, specifically the National Water Center. I am a software engineer, and Jason is, what is your official title, Jason? Sorry, I should know this.
My official title is scientist, yeah, or physical scientist. Don't worry, nobody else knows what I do here either.
Well, today we would love to introduce to you HydroTools, a tool for retrieving and evaluating hydrologic data. So what is HydroTools? HydroTools is a grab what you need ecosystem of opinionated Python packages for retrieving and evaluating hydrologic data. We built HydroTools to be intentionally predictable and familiar. Just like a toolbox, we wanted the ability to grab the right tool for the job, but not have to relearn how to use the same tool over and over and over again. Our packages use and return data structures familiar to data scientists, and all share a canonical data format that enable tools to work together or separately. You can go to the next one, Jason. Across our ecosystem of tools, we've implemented a consistent set of APIs that are predictable and potentially even boring. As you can see, many of our tools look and feel the same, and they all return the HydroTools canonical data format. All methods have the same. All methods have type hints and sensible default values where appropriate that enable a friendly and exploratory IDE experience. Just like if you were using pandas or GeoPandas, we expect HydroTools to handle data you pass in like you would expect it to. We want HydroTools to be predictable. This means high compatibility with pandas, NumPy, and built-in Python types like dictionaries, lists, etc. Lastly, we want HydroTools to be scalable. Python has come out with great primitives for doing asynchronous processes as well as doing multi-processing. And a lot of the workflows that we are asked to do require crunching a large amount of data. So our data clients take advantage of Python's asynchronous async IO package, as well as multiprocessing, and where available, we are compliant with other packages like Dask, and do as much client-side data caching as possible, which means when you get the data once, you don't have to get it again.
Okay, so I'll hop in here. I'm assuming I'm audible. Let me double check. All right,
Yeah, you're good.
So as you can imagine, if you've done any like Python development or any development, simple interfaces often hide a variety of sins. You know, one of the motivations for Hydro tools, you know, apart from being able to add a Hydro prefix to yet another word, was we had this issue in the Office of Water Prediction, right, where we have the National Water Model. It's a huge continental scale model, and so we often have to pull tons and tons and tons of data, right? So we don't just need USGS observations from a single site. We need them from all the sites, right, that are in our model. In addition, if you've ever worked with National Water Model data, you're probably aware that it's basically a mess. And difficult to work with. So the challenge we kept running into was first that our scientists who needed to conduct evaluations of the National Water Model spent most of their time just getting the data. The next issue we kind of ran into as we started simplifying things was that we needed some type of canonical data format, right? So we had kind of chosen data frames as our default way of passing data between packages. But with data frames, you need some standard to name columns and have kind of a standard for the data types associated with those columns. So our solution was to have a set lexicon of special words that can only be used, you know, that if this column is present in your data frame, you know what it is and what it refers to. And this is defined in the Hydro Tools README what each of these are. So this is kind of the other side of trying to simplify things. It is having this canonical data format, at least for data frames. Currently, the packages we have are, as I said, a National Water Model client that defaults to the data on Google Cloud Platform. And to be clear, most of our packages right now skew towards Streamflow. So retrieving Streamflow, although our InWIS package can retrieve, I think, anything from the instantaneous values service. But National Water Model Streamflow for sure. And then the InWIS client, as I mentioned. We also have a few signal processing methods, which I'll demonstrate here shortly. A variety of evaluation metrics in a metrics package. And then recently, thanks to Austin's hard work, we have a client to start incorporating social vulnerability indices into evaluations. And this client also retrieves that type of data from the CDC or from their endpoint in the canonical format that we use. So with that, I'm actually going to hop screens.
I think you're on mute, Jason.
Yeah, you have to click the button, you have to uncheck something. Okay. All right, am I audible now?
You're great.
All right. So this is a demonstration that we originally presented at the 2021 AGU fall meeting. And this just kind of demonstrates how to use some of these tools that we've got in HydroTools, and kind of takes you through maybe a typical national water model evaluation exercise. So the first thing we look at is getting simulation data. So in this case, we're retrieving what's colloquially called the open loop or the no data assimilation cycle of the national water model. So it's a simulation that's ran once a day. And so here we're just setting up the data client, and then there's some more pre-setup, and then the actual get happens here. So here I'm just collecting several simulations over the last 30 days. And what this is doing on the back end is actually going out and getting the associated, I don't know how many hundreds of files associated with this 30-day simulation, and then packaging it all up as a convenient data frame for the user. Then down here, it's taking what we're doing here is we're taking a look at the USGS sites that are in those data, and then going and get the associated observations from USGS, from INWIS, using our client tool. And it's a similar thing here. So here we're setting up the client, and then we're doing some extra work around it. But then this is the step where we go and actually get the companion observations for those simulations. And then here's just a little function that combines those data together into a pair. So here we have, I think in this case, this is actually a data frame with 7,000 some odd USGS sites, along with 30 days of observations and national water model simulations. And so in the past, everything up to this step would be its own project inside the Office of Water Prediction in my division, just getting to the point where we have paired data. Whereas now with HydroTools, we can kind of just do it. And then now we can kind of move into the evaluation side. And here I've chosen to focus on a single site, which is my favorite USGS site, called Little Hope Creek in North Carolina. And here's an example of just plotting up the data using standard Python plotting library, matplotlib. And then here we're using some things from the metrics package, where I create a contingency table given some threshold just so that I can generate categorical type metrics like these: probability of detection, probability of false detection, frequency bias, things of that nature, and then even non-categorical metrics like normalized Nash-Sutcliffe. I think we also have KGE and root mean squared error and all that stuff in there. And then you can also do a little bit more sophisticated things like the event detection signal processing algorithm I alluded to earlier, where that will go through and look at a stream flow signal, and given the parameters, we'll try to identify periods where there's likely a rainfall driven runoff event. And once you have those periods identified, then you can do things like a peak flow analysis. Where is that plot? Oh, there's not here. All right, like a peak flow analysis, for example. So here I've got start and end for each period identified, and its associated time of peak and total volume and its actual peak magnitude. And then once you do that, if you do that for both the observation and simulation, you can do an evaluation where you focus on your peak discharge errors or your volumetric discharge errors. So these are pretty standard steps that we do when we're evaluating the national water model. Let me go back to that other screen, and this time I will remember to uncheck the box. All right. Okay, and then so I'll wrap it up here. That's kind of all we had to show. I believe one of these, goes to the contribution guide, and the other one actually goes to our GitHub repository, where we have several open issues. And that's it. Thank you. I'll pass it on to Ryan.
Thank you so much. All right, and our last speaker, Ryan Johnson, take it away.
All right, great job, guys. It's been great so far. All right. Okay, yeah, my name is Ryan Johnson, and today I'll be my talks on characterizing the state of the snowpack with the National Snow Model. So why model snow? Seasonal mountain snowpack is a critical water resource throughout the Western US. And it acts as a natural reservoir by storing precipitation throughout the winter months and then releasing it as snowmelt during the spring and summer. Around October, snow begins to fall and SWE, or snow water equivalent, begins to accumulate, especially at the higher elevations. And over the course of the winter, the snowpack can be several feet thick and store several inches of water. At some point during the spring, the snowpack reaches a peak SWE, and then it begins to decline as snow begins to melt. And that date of peak SWE marks the beginning of melt timing. During the summer months, the infiltration of meltwater increases soil saturation, and it makes its way into streams. This meltwater becomes runoff, then serves as the primary freshwater source for major streams and rivers in the West, and it's then captured downstream by diversions or reservoirs, just as we've seen today in the discussions. And then for many places in the West, snowmelt composes the majority of the annual water budget. And this water goes and then serves millions of people for multiple types of uses. So with this direct connection between snowpack and stream flow, and then the resulting supply, there's a strong research need for characterizing the state of SWE. And as we see right here, a figure from the NRCS, there's, one of the products is a SWE mapping product. And this is for just last week, we had a bunch of storms out here in the West. So SWE modeling challenges. Real-time SWE estimation remains challenged by significant spatial variation and precipitation, temperature, elevation, etc. And that creates a extreme heterogeneity in SWE and snow cover in these topographically complex mountain regions. And then, for example, here's a picture from a helicopter flight in Little Cottonwood Canyon, just east of Salt Lake City. And it just demonstrates the variability in snow cover. On kind of that center right side of the figure, it's south facing and there's no snow. On the left, there's Alta and Snowbird. Those are north facing ski resorts and have multiple feet of snow. And then we also see a general trend of increasing snow depth as elevation increases. And so there are physically based models to estimate SWE. Popular ones are Snow 17, iSnowbell, etc. And they're often nature prevents the modeling of heterogeneous SWE distribution. So we saw an opportunity to integrate advancements in machine learning and then apply them to SWE modeling. And a couple of items that we wanted to address were what observational products are reliable for operational use. We wanted to evaluate multiple model formulations to identify ideal prediction algorithms. We wanted to evaluate model performance to an assortment of in-situ observations. And then we wanted to create an extension products to help inform Western water resources management. We wanted to model to be a high resolution, 1 kilometer grid spatial to be exact. And then we wanted the model to not be computationally intense. So the predictions needed to be able to run on a simple laptop. And then lastly, we wanted the modeling workflow to be completely transparent using open source software with the MIT license. The majority of the researchers on the project are all avid skiers, and we know that there's different snow characteristics and they vary from region to region. For example, there's coastal, continental, intermountain. It's kind of the general trend as we go from west to east. And then we know we want to use in-situ snow telemetry, known as SNOWTEL data. And then to address the heterogeneity of snowpack from a modeling perspective, we broke the model down into 23 subregions. And then we wanted to create 2 types of feature groups, stationary and then dynamic. And the stationary features include like site characteristics of each 1 kilometer grid. And so we have, for this demonstration of our project, we did 20,000 square kilometers. And then each of those square kilometers includes aspect, slope angle, northness, and then lat long as those site characteristics. The dynamic features account for near real-time conditions. So that's like, we have week ID, which begins October 1st, the start of the water year. And then we use SNOTEL and then California Data Exchange Center, or SWE observations. So we have, real-time SWE, we use the previous week SWE, and then we create a metric called Delta SWE that communicates that difference between this week and the previous week. And then for this experiment, we also evaluated different MODIS and aqua remote sensing data products. And then all the data was scaled from 0 to 1. And then we QC the data by removing bad observations. For the algorithm evaluation, we built models for XGBoost, light gradient boosted model, and then a deep learning multi-layer perceptron network. And then for feature selection, we evaluated multiple dimensionality reduction methods, and they end up finding that recursive, box went to the wrong spot. Recursive feature elimination was our optimal feature engineering, feature elimination algorithm. We did parameter tuning on the MLP models. We looked at different layer node configurations for select regions. And we did hyperparameter grid search for the tree-based models. And then for the model training, we used 75% of the 2013 to 2019 observations. This is over 200,000 observations. And then this project is also part of the Snowcast Showdown. And that was basically evaluated for near real-time performance during the 2022 water year. Model evaluation was on that 25% holdout data set. And we used the coefficient of determination and root mean squared error to gauge the performance for each region. And our LQBM model produced lesser RMSE compared to the MLP during testing. However, our final model testing during that real world evaluation showed that an increasing SWE during last year's January through March, when we had a 2-month snow drought. We had no precipitation really in the West. And that tree-based model showed an increase in precip or a SWE accumulation. So it kind of demonstrated the errors and limitations of some machine learning algorithms. And then so the research indicated the MLP model, it captured that snow drought. And so that's what we selected for our model. All right, so now the fun part. Right now the model is set up to be an interactive Jupyter environment. And writing the model requires input the date. So right here, we say I ran this the other day, 11/12, and it begins on October 1st with 0 SWE. So we get that get modeling data function. It retrieves all the necessary SNOTEL and CDEC SWE observations for the input date. And then this step is going to be the most time consuming. It takes usually between 5 and 7 minutes. We have a data processing function that takes all the ingested data, puts it into the correct format, and that includes filling NA, scaling, and builds a data frame to go for the model predictions. Our predictions run through all 23 regions and takes less than 1 minute to predict over 20,000 square kilometers of mountainous SWE. We convert the predictions into a GeoPandas data frame, and that supports geographic processing to other spatial scales. So today I'll show you different HUC levels, and for our future work, and Austin and Jason will be excited, is we're going to be putting into the next-gen National Water Model HydroFabric. And then just for the interactive plot or interactive script, we have a interactive plotting with fully choropath-based map of the 1 kilometer SWE predictions, as well as we demonstrate HUC8. And then we compress all the data into a netCDF file, and that includes all the different spatial resolutions. And then I'll show some interactive mapping real quick. So here's our predictions for 11/12. We have Lake Tahoe right here. Multiple, you can see that going out to the Southern Sierras. We can zoom out. We can go, we have a lot of work in Colorado, up in the Wind Rivers. And then we also can take mean SWE from all these areas as well. And it's all interactive at the moment. So far, evaluating what we've done so far, we see it demonstrates a connectivity between sites and the previous week's observations. It's fast. We've been able to, it takes about 15 minutes to ingest the data, process it, make predictions, visualize it, and then save the files in a netCDF format. It's 100% open source. We're looking at the potential to integrate other data sources. Then we're looking, targeting some operational applications, national water model, using reservoir management, et cetera. And then our next steps, we're going to be evaluating some other algorithms, probabilistic and physics-based approaches. We want to extend our trading period. We definitely think there's some potential for overfitting and using that 75-25% random split. So we're going to try with hold one out for the year training. And then we're deploying as an interactive app currently. So right now we're running this on a Threads server with Tessus and trying to get everything live. So the model runs automatically. And then we can, have a dashboard. We can click on our Cairo website so you can see what the model's predicting at the moment. And with that, I am done. I'd like to thank everyone on the project. Our GitHub is through the Alabama Water Institute. I thank all our collaborators. And here's a beautiful picture of my partner, Dane, doing some snow observations in northern Utah. And with that, I'll hand it back over to Julia to close this out.
All right, thanks so much. Thank you, Ryan, and thank you to all of our speakers today. I recognize it's hard to condense all of the work that you guys have done into 10 minutes, but we really appreciate it. We have a couple of questions that are open in the chat or in the Q&A, excuse me. Please, audience members, feel free to keep those coming. We'll get to as many as we can. We'll start with the ones that are currently open and then maybe go back to some of the ones that have already been answered to get some more insight if there's time. Okay, Ryan, first one's for you. How do you hold out the SWE data randomly for sites, or do you hold out a full region?
It's randomly for the sites currently. We use the 70. So for each of those 23 regions, there is a 75-25% split, or use the 25% for training, and then testing on the remaining 25%. We do feel the overfitting. There's a lot of connections within year, and the model is picking that up. And so that's why as we continue to evolve the model, we just want to hold multiple years out, so that today's value in a training data set does not influence the following weeks if that was a potential for prediction.
Great, thanks. Okay, Shengyi, do you have to manually add the routing scheme in the configuration file? If so, is there a way to automate this process?
Yeah, that's a good question. So user don't need to define the entire routing schema for the entire system. For example, you just need to define partial routing schema. For example, you have a node at a downstream, and you need to define what's the corresponding upstream outlet that will contribute to the stream flow at this specific downstream routing outlet that you want to calculate the stream flow. So, and we also, in this package, we also provide a model builder. So you can use that tool to help you to check is there any mistake inside the configuration file, and use that to semi-automatic build a hydrological model that can run by the HydroCNHs.
Great, thanks. Okay, one for OWP team here. Oh, looks like it just got answered, perhaps. Yeah, is the output from the OWP Hydro tools supplied as multiple data frames? If so, is it feasible to concatenate the data frames? Sorry, new word to me.
Yeah, you did great, Julia. So I think all of the methods from all the tools that we have only return single data frames, but it is totally feasible if that fits your use case to call multiple methods multiple times and then concatenate them together. Should work just fine.
Yeah, I would say part of the canonical standard was any method named get will return a single data frame. And in fact, if, for example, with the NWIS tool, if you're asking for multiple sites, it's concatenating the data frames on the back end.
Great, thanks. Okay, Carlos, I've noticed you've already answered one of the questions in the Q&A, but but let's return to that really quick so we can learn a little bit more from your tool. Can HydroLink support model calibration using this platform, or is it only for the analysis of model results and visualization? Does it work for any hydrologic model?
Yeah, right. So as of right now, as I think I replied, it's mostly for results and visualization purposes, but we do have some tools inside, right? So tools like calibration metrics, efficiency metrics, and whatnot, NSE and whatnot. We are working towards integrating more calibration validation schemes towards our hydrological models. But then again, this is not constrained by the tools that are available within the framework right now. The idea of HydroLink is that if a user wants to add their hydrological model inside of it, they can do so as well very easily. Just plug in as a function into the module itself. So we definitely we'll add more into the framework, but it's not a constraint.
Great, thanks. Ryan, circling back to you, we have a long question here. The question is, do I understand that you're using a grid-based domain decentralization for the snow, or discretization for the snow simulations? If so, how does the grid size compare to the size of the topographic features that influence snow formation and melt? And then second question, following up, would your approach also work on a domain that's discretized into irregular elements that follow topographic features? So separate model elements from north and south facing slopes, for example.
So I would say the answer is yes. And I was trying to type as fast as I could to answer the question in the Q&A. This was part of the Bureau of Reclamation Snowcast showdown, and they wanted a 1 kilometer grid as far as their model resolution. I honestly do not know how they created a mean SWE for a 1 kilometer grid. Like, that information was not presented to us. I would actually think they probably did just manual observations, like on a snow course assessment, to get some of our training data along with a lot of SNOTEL observations. But there's no reason that you couldn't develop a regionalized model, like that image I showed in Little Cottonwood Canyon. You could do a 50-meter resolution if you wanted to get out there and take a bunch of different measurements surrounding the whole watershed to capture the different topographic features, valleys, ridges, like you're saying. It just needs the training data. And the way that, we used 20,000 points, and we took their geographic average from the 4 corners of that square to get the characteristics of that location. That same process could be done for a smaller resolution. Like I said, it all depends on the training data. And if somebody wants to work to help develop the model, we're happy to connect and see where the model can go from here.
Great, thanks so much. All right, jumping back to Shengyi, how does a agent-based model compare with traditional water management models such as Riverware and Modis-IM or Modison? It's always a guessing game with some of these models for me, but can more complex hydrologic models such as a fully distributed hydrologic model be used in this framework?
Right. So for the first question, the ABN, what is the difference between the ABN and the traditional Riverware model is that for a traditional model, we usually need to provide the input data to describe, okay, how the reservoir releases the data, or we can set up a simple operational rules into those software. But the ABN is more flexible to incorporate the psychological factor into our models. For example, we can define how farmers decide to decrease the diversion water according to the weather forecast or the economic factor that will change their crop decisions, and that might change their diversion behavior. And by using ABN, we can model that kind of social behavioral change. And whether this model can incorporate the fully distributed hydrological model, I would say it has the potential because this is a semi-distributed model. So for the fully distributed model, you basically just create a really fine subbasing into a grid base, then it somehow change the semi-distributed model into a distributed model. But of course, you need to further modify the package a little bit to enhance the computational efficiency for the fully distributed model.
Thank you so much. Well, we're at the hour here, so we'll wrap things up. But thank you to everyone who attended for attending this series. All of the recordings from this whole series will be posted on the CUAHSI YouTube channel. Thank you again to all of our speakers for joining us today and for sharing all of the work that they do. And a shout out to Clara, who convened this series and invited all of our speakers here today. Have a great rest of your week, and thanks for joining. Bye.
Bye.